were asked to draw an airplane today, most people would probably draw something very similar. A fuselage, two wings extending to the left and right, a tail at the back, and engines either in front or on the sides. This seems to be the standard answer to what an airplane should look like. And for more than a century, that answer has remained remarkably stable. From wood and fabric aircraft to metal airliners, from propellers to jet engines, from low-altitude flight to the supersonic age, the materials, speed, and power systems of aircraft have all changed, but their basic outline has rarely been overturned. Yet at the beginning of aviation history, this was not the case. Airplanes did not have one fixed standard shape. People did not yet know what kind of machine the future sky would belong to, so they tried many designs that look extremely strange to us today. Among these ideas, one path was especially unusual. It was not satisfied with simply letting the wings stretch out to the left and right. It tried to bend the wings back, turning them into a circle, a ring, a box, or even a fully connected frame. These aircraft looked like barrels, donuts, and flying boxes, making it easy to mistake them for machines from the future. This is the closed-wing aircraft. Interestingly, this path never truly disappeared. From the earliest days of aviation, to Cold War vertical takeoff experiments, to today's concepts for fuel-efficient airliners and drones, closed wings have reappeared again and again, but they have never become mainstream. Why? Why has an aircraft shape that looks so unusual and even seems closer to the future appeared repeatedly throughout aviation history, only to retreat back to the margins? In this episode, we look back at the brief history of closed-wing aircraft, a century-long experiment that tried to rewrite the shape of the airplane.
If I told you that for more than a century, most aircraft wings have carried a kind of incompleteness, would you believe it? From the Wright brothers' wooden biplane to today's Boeing and Airbus airliners, most aircraft have followed the same basic structure: a fuselage in the middle, wings extending to the left and right, and then ending at both tips. This structure looks natural, and it has been extremely successful. But this is exactly where the problem begins. The wing has an end. When an aircraft is flying, the air pressure below the wing is usually higher than the pressure above it. At the wingtip, this high-pressure air from below tends to curl around toward the low-pressure area above. This motion causes the air near the wingtip to roll into a vortex. This is called a wingtip vortex. If you have ever seen an aircraft taking off or landing in humid weather, you may have noticed two white trails behind the wings. Those are not smoke. They're traces of water vapor condensing after the air has been disturbed by the wing. Wingtip vortices create extra drag, known as induced drag. To generate lift, an aircraft must spend energy, and part of that energy is lost to these wingtip vortices.
For aerospace engineers, the wingtip has always been a problem.
As long as a wing has a tip, air can curl around it. As long as air curls around it, vortices will form, and when vortices form, the aircraft must consume more energy. So ever since the birth of aviation, engineers have been looking for ways to reduce this loss. One of the most direct methods is to make the wing longer. The longer the wing and the greater the wingspan, the smaller the influence of the wingtips on the overall lift system usually becomes. This is why gliders often have long, narrow wings. The upward curved winglets on modern airliners are also designed to deal with a similar problem. But wings cannot be extended indefinitely. Wings that are too long create problems with structural weight, strength, airport parking, takeoff and landing, and manufacturing. This led to a more radical idea. If the wingtip is the source of the problem, Can a wing be designed without a conventional wingtip? Can the wing be bent back and connected to another lifting surface? This is the basic logic behind closed-wing aircraft. They were not created simply to look strange. What they were really trying to solve was the aerodynamic loss caused by the ends of conventional wings. The German aerodynamicist Ludwig Prandtl studied how to reduce induced drag in aircraft lift systems. In his related theories, one important direction was to find a more efficient lift distribution, allowing an aircraft to reduce drag as much as possible within a limited wingspan. Later designs such as box wings, joined wings, and Prandtl wings can all be understood within this same problem. Their goal was not to turn aircraft into circular toys. They were attempts to use a different wing structure to reduce the losses caused by conventional wingtips. In simple terms, the wing of a conventional aircraft is a line extending sideways. A closed wing tries to connect that line back onto itself, forming a ring, a box, a diamond, or a closed framework in which the front, rear, upper, and lower lifting surfaces support one another.
But when closed-wing aircraft first appeared, people did not yet understand the existence of wingtip vortices. In the early 20th century, airplanes did not yet have a fixed shape. The aircraft layout we are familiar with today had not yet become the only answer. Flying machines at the time looked like kites, gliders, boats, birds, or experimental structures made from wooden frames and fabric. At this stage, any shape that seemed capable of producing lift had a chance to be tested. The annular wing was one of them. In 1906, the French aviation pioneers Louis Blériot and Gabriel Voisin built a very unusual aircraft. It was the Blériot 3. This aircraft barely looked like the airplanes we know today. Its central fuselage resembled a small boat with an oval ring-shaped wing surface at both the front and the rear, making it look like two giant barrels connected in series. This was not a design created simply to attract attention. Blériot and Voisin hoped that this annular wing would provide better stability and perhaps offer certain structural and aerodynamic advantages in early flight. The idea was bold, but the reality was difficult. The Blériot 3 was not successful. Later, it was modified into the Blériot 4 with changes to its structure, but the results were still unsatisfactory. These early annular wing aircraft revealed a problem. Bending a wing into a circle does not automatically make an aircraft fly better. A circular structure may look complete, but it also adds weight. For the weak engines of the time, every extra kilogram was a major burden. In addition, the front and rear wing surfaces could interfere with each other, making the airflow more complex and the aircraft harder to control. A few years later, similar attempts were made in Britain. Around 1910, an annular wing aircraft known as the kitchen donut attracted attention. Donut was a very direct name because its wing looked like a circular ring. Unlike a conventional aircraft, which spreads its wings out in a straight line, this design arranged the lifting surface into an almost circular structure. From the outside, it barely looked like an airplane. It looked more like a flying ring being pulled along by an engine and a seat. Early designers of annular wings often believed that circular wings could provide better stability because they did not have obvious left and right wingtips like ordinary wings. The structure also looked more compact. In crosswinds, it seemed possible that such a design might hold its attitude more easily. But many of these judgments came from intuition, not mature aerodynamic calculations. Engineers at the time did not have today's wind tunnel data, computer simulations, or flight control systems. They could only build, test, crash, repair, and modify.
After that, the annular wing entered a more serious phase. In Britain, Cedric Lee and G. Tilghman Richards continued to develop annular wing aircraft. They built a series of Lee-Richards annular wing aircraft. One of the most representative examples was the Lee-Richards annular monoplane. Unlike the Blériot 3, with its two large ring-shaped wings at the front and rear, the Lee-Richards design was closer to a real airplane in the modern sense. It had a fuselage, an engine, and an annular wing arranged around the fuselage. In the 1910s, these aircraft were tested in flight. Records show that under certain conditions, they could indeed leave the ground and display a degree of stability. But the problems remained. The first was weight. Circular or closed structures required more material and support. The second was drag. The airflow around an annular wing was not always smoother than that around a conventional wing. Different parts of the wing surface could interfere with each other. Airflow passing over one surface could then affect another. The third was control. On a conventional aircraft, the wing, tail, and control surfaces are relatively clear in their roles. A pilot knows which parts are responsible for pitch, yaw, and roll. But on an annular wing aircraft, the airflow distribution is more complex, and the control response is harder to predict. The fourth was manufacturing. Early aircraft were already fragile. Wood, fabric, wires, and simple engines had already pushed engineers to the limit. Adding a complicated annular wing structure only made the task more difficult. So the annular wing soon found itself in an awkward position. It could fly, but not well enough, and not well enough to replace the conventional wing. In an age when aviation technology was developing rapidly, that was enough to decide its fate. Early aircraft engines were too weak, the materials were too light and fragile, and control systems were still immature. Under these conditions, the weight, structural complexity, and control problems brought by annular wings far outweighed their possible benefits. By comparison, the conventional layout was simpler and easier to improve. As a result, the combination of fuselage, left and right wings and tail quickly became the mainstream answer for the aviation industry. Annular wings retreated to the margins. But the idea did not disappear. Although the early flying barrels and donuts failed, they left behind one line of thought. A wing does not necessarily have to end at both tips. Decades later, this idea would reappear in a more radical form.
By the 1950s, engineers brought the annular wing back once again. This time, it was used to explore a practical problem: vertical takeoff and landing. After the Second World War, the jet age officially began. Aircraft became faster and faster, but they also became increasingly dependent on airports and runways. For military aviation, however, the runway itself was a weakness. If an airfield was damaged, the aircraft could lose its combat effectiveness before it even took off. So, in the early Cold War, many countries were asking the same question: could they build an aircraft that could take off vertically like a helicopter while also flying horizontally at high speed like a jet aircraft? Against this background, the French company SNECMA proposed a very bold design: the SNECMA C.450 Coléoptère. The name Coléoptère comes from French and means something close to beetle. The Coléoptere's enormous cylindrical wing was completely different from that of a conventional aircraft. When parked on the ground, it looked like a vertical cylinder. Its fuselage was surrounded by a huge cylindrical wing. The pilot sat at the front of the fuselage, while the engine directed its thrust downward, allowing the entire aircraft to take off vertically. After climbing into the air, it would then attempt to transition from a vertical attitude into horizontal flight. In the history of closed-wing aircraft, the significance of the Coléoptère was not only that it attempted vertical takeoff and landing. More importantly, it developed the annular wing into a cylindrical structure that surrounded the fuselage. From the perspective of closed-wing design, it was almost one of the most extreme versions of the annular wing.
This design had several purposes. First, it reduced the aircraft's lateral width. If an aircraft was intended to take off and land vertically, engineers did not want it to have a long pair of conventional wings. Second, the cylindrical wing could provide lift during horizontal flight. In other words,
It was not just an outer shell, it was a real lifting surface. Third, it could be combined with a jet engine and a vertical takeoff layout, making the whole aircraft look more like a new kind of flying machine that did not depend on runways. But this is also where the problem appeared. The Coléoptère placed too many tasks on its cylindrical wing. It had to function as a wing, adapt to vertical takeoff and landing, and help the aircraft transition from a vertical attitude into horizontal flight. This made the airflow, control, and flight states extremely complex. When the aircraft took off vertically, the wing faced one airflow condition. When it flew horizontally, the wing faced another. During the transition from vertical flight to horizontal flight, the airflow kept changing. This was one of the hardest parts of the design to manage. Closed wings were originally intended to gain aerodynamic advantages through special structures, but on the Coléoptère, the closed structure actually increased the complexity of the entire system. In 1959, the Coléoptère lost control during a test flight and crashed. The pilot ejected safely, and the project soon came to an end. In the history of closed-wing aircraft, the Coléoptère was a boundary case. It pushed the annular wing to an extreme position, and it also demonstrated one of the most common problems of closed-wing design. It could fly, and it did have real strengths, but each strength often brought several new engineering difficulties at the same time.
Many early closed-wing designs tried to shape the wing into a circle, but circular wings were not easy to handle. They were structurally complex, heavy, difficult to manufacture, and their airflow was hard to predict. So later, closed-wing aircraft did not continue only along the path of the ring. Engineers began to change the way they thought about the problem. Could the wing be folded into a frame? As a result, closed wings gradually evolved from circular forms into box wings and joined wings. A box wing can be understood simply as an aircraft with two sets of wing surfaces, either upper and lower or front and rear, connected near the wingtips. In this way, the wings are no longer two separate surfaces extending outward, but more like a closed frame. From the front or the side, it can look like a flattened box, which is why this design is called a box wing. A joined wing, on the other hand, usually connects the front wing and the rear wing. It does not necessarily form a regular box, but it still allows the wing surfaces to support one another, creating a closed or semi-closed structure. The point of these designs is to achieve the goals of closed-wing aircraft in a more practical way, to reduce wingtip losses as much as possible within a limited wingspan, while also improving structural efficiency. Compared with early annular wings, this was a clear change. Early annular wings were more like attempts to create an entirely new aircraft shape. Box wings and joined wings, however, were more like a rearrangement of the wings on an otherwise conventional aircraft. They kept the fuselage, the engine, and the basic logic of flight, but turned the wing from a single horizontal line into an interconnected system. One representative example was the Ludwig Stratos from the 1980s. It was an ultralight aircraft designed in Australia. What made it unusual was that its wing was not a conventional left and right layout. Seen from above, its wing surfaces formed a diamond-shaped frame. The front and rear wings were connected to one another, creating a clearly closed layout. The frame of the Ludwig Stratos could provide lift while also allowing the structure to support itself. It brought closed-wing design away from the early idea of circular rings and towards something lighter, smaller, and closer to a personal aircraft.
In modern civil aviation research, closed wings have appeared in forms that are closer to airliners. One of the most frequently mentioned examples is the Prandtl crane. As mentioned earlier, the core of Prandtl's theory was to find a more efficient lift system within a limited wingspan. The Prandtl plane can be understood as a modern airliner extension of that idea. It no longer turns the wing into a ring.
Instead, it usually uses two layers of wing surfaces, arranged with a front and rear offset and connected at the wingtips. As a whole, it looks like an aircraft with a double-layered closed wing. The goal is to reorganize the lift distribution between the wing surfaces without greatly increasing the wingspan. For large airliners, wingspan cannot be increased without limit. Airport stands, taxiways, jet bridges, and hangars all restrict aircraft dimensions. So if efficiency can be improved without significantly increasing wingspan, the box wing becomes attractive again. It can create a more complex lift system within a limited width. In theory, it may reduce induced drag, improve the lift-to-drag ratio, and therefore lower fuel consumption. Structurally, the connection between the upper and lower wings may also help share loads and increase rigidity. This is why box wings repeatedly appear in concepts for future fuel-efficient airliners. However, box wings and joined wings do not solve every problem. A conventional aircraft mainly has one primary wing system, and the airflow relationship is relatively clear. Box wings and joined wings have upper and lower wing surfaces, front and rear wing surfaces, and connecting structures. These parts influence one another. The upper wing can interfere with the lower wing, and the airflow from the front wing can affect the rear wing. If the design is not precise enough, the drag that was supposed to be reduced may be replaced by new interference drag. The structure is also more complex. Once the wings are connected to each other, the load paths become longer and harder to calculate. How the entire frame deforms during turns, turbulence, landings, and high-speed flight all has to be verified again. Manufacturing and maintenance costs also rise as a result. In addition, conventional wings have been industrially optimized for more than a century. From design and production to maintenance and pilot training, mature systems already exist. Box wings and joined wings require new structural layouts, new manufacturing methods, and new safety verification. This is the current position of modern closed-wing design. It is far more rational than the early annular wings, and it is also closer to reality. But for it to truly enter the mainstream, it still has to pay a very high system-level cost. At least for now, that road remains long.
Looking back at the history of closed-wing aircraft, we can see that it was never just a strange idea. It always had a clear goal: to reduce the losses at the ends of the wings and to make aircraft more efficient within a limited wingspan. That is why it has appeared again and again. Early engineers bent the wing into a ring. During the Cold War, French engineers turned it into a cylindrical wing. In the modern era, closed wings have reappeared as box wings, joined wings, and future airliner concepts. But every advantage often brings a new cost. A ring adds weight. A cylindrical wing makes airflow and control more complex. Box wings and joined wings may improve lift distribution, but they also bring new problems in structure, manufacturing, maintenance, and certification. For large commercial aircraft, closed wings also have to face more practical limits. Airport stands, jet bridges, maintenance procedures, emergency evacuation, and airline costs cannot be solved by aerodynamic formulas alone. So closed-wing aircraft are more like an expensive luxury in aviation history. In the pursuit of extreme efficiency, they accidentally locked themselves inside a perfect circle. That circle is beautiful, and it has logic, but aircraft cannot fly only in theory. They must enter factories, fit in airports, pass safety regulations, be purchased by airlines, be flown by pilots, and be inspected again and again by maintenance crews. This is the most awkward part of the closed wing. After more than a century, closed wings still reappear at the margins of aviation history. They have never truly disappeared, and they have never truly won. They are more like a constant reminder. The sky can accept many shapes, but the aircraft that truly remain
must pass the tests of both air and reality.
This is BHE, Brief History of Everything.